if you can't be right here. I do the same thing I told you that I never would. Told you I changed, even when I knew I never could. Know that I can't find nobody else as good as you. I need you to stay, need you to stay. Do the same thing I told you that I never would. Told you I changed, even when I knew I never could. Know that I can't find nobody else as good as you. I need you to stay, need you to stay. I need you to stay, need you to stay. You gotta go and get angry at all of my honesty. No, I try, but I don't put you up with apologies. I hope I don't run out of time, cause someone call a referee. Cause I just need one more shot, half a game.
Hey, good morning, beautiful. Week 4, how y'all feeling? Are you tired yet? You good? How's the lab going? You guys sound scared. The lab. Learn something yet? Learn something new? Have you boiled water? Yeah? Yeah. All right. When's the exam 2? Next Tuesday, right? 16th. Okay, next Tuesday. All right. Almost done with the covering exam 2. We'll talk about exam 2 later this week, maybe on Thursday. Okay. All right, you guys ready? Make some noise, huh? Wow, okay. All right. People on Zoom, how you doing?
Good.
Oh, we got one person. Okay, all right. Sounds pretty good. All right. Everyone say hi to people on Zoom. Okay. Well, they don't say hi back. Okay, all right. That's not happening. You've been through COVID, right? How were you in high school? Something like that? COVID? Okay. How's the school during COVID? Was it fun? You get to stay home. How's that? Yeah, actually kind of nice. Did you learn anything? Nope. Okay. All right. That's a Zoom online education, huh? All right, let's review. Okay. We have learned 5 reactions. You know the mechanism of those? Have you been following me throughout the semester so far? Do you make second note? Do you know what second note is? Okay. All right. Did you put this 5 reaction in your second note? I hope you did. Okay. I hope you did. Hopefully you know which how each reaction work. Okay. All right. We also learned the effect of the substituent on benzene. Okay. This is for when you do a reaction. All right. Now let's review. Okay. These top 3 are activating groups. What does activating group mean? Faster reaction or slower reaction? faster reaction. When you put any of this onto benzene, that benzene is faster by how many times compared to a regular benzene, an unsubstituted benzene, okay? All right, down here we have a deactivating groups or deactivators, so the rate is slower, okay? All right, let's start with the top two. The top two rows, these are the electron donating groups through resonance effect. Do you know how? How do you know this is a resonance effect? We look for the electrons right next to benzene, conjugated with benzene. Okay, should be able to draw arrows like that. All right. Now the second one right here, the second row is less donating than the top row. Can you tell me why? The top one is the most activating group, the strongest electron donating group. The second row is less. How come? See, the lone pair is conjugated with the benzene, but the lone pair on the second row also conjugated with electron withdrawing group. Are you all see that? Okay, so these are less electron donating. Okay, next one, this one just hyperconjugation. Okay, so much less in resonance. All right, move to the deactivating group. This is the weak deactivating group because resonance effect are not as good. Inductive effect is up there. Okay, so the two effect against each other. So as a result, this guy just weak activating group. Down here, these are moderate deactivating group, electron withdrawing group. And at the bottom right here, we have a nitro group, one of the most powerful electron withdrawing group, inductive effect, resonance effect, pull from the benzene. Okay. All right, down here, the last three right here, this one by electronegativity, all through inductive effect, a bunch of electronegative atoms on the carbon next to benzene, And the last one, we have ammonium ion, positively charged nitrogen. Okay. All right. The top four rows all the way to halides, okay, all the way to halide. These are ortho and para directing groups, okay, which means that when you do reaction, the incoming electrophile goes to either ortho and para, and mostly para because it's their hindrance on ortho. Are you following on that? Okay, and down here we have the meta directing group, okay, okay. The strength go from weak to strong, like that. Okay, on exam you have to be able to spot if you have electron donating group, electron withdrawing group, and kind of relatively rank their activity. Okay, let's start with so we have 4 compounds just to practice, just to warm up your brain. All right. 2 of these are electron donating groups, and 2 of these benzene have electron donating groups. Which one? A and B. Can you see that? A and B? And then we have C and D are withdrawing group. Okay? Look at between A and D. Look at the groups on benzene between A and D. Which one is a stronger donating group? A or B? Should be B. Okay? What's wrong with A? The lone pair on the nitrogen is conjugated with the benzene and an electron withdrawing group. You see that? Okay, so A should be less activating than B. If you see B, all lone pair in B goes directly into the benzene ring. Okay, so B should be more activating than A, which means speed of reaction faster in B than A. That's what it means. Okay. All right, we got C and D. Okay, what type of deactivating group is C? Weak, moderate, or strong? You're going to look at the feature, what's they have in it. Okay? If you see that there's the electron was a double bond next to the benzene, and this double bond connect directly to the electronegative atom, they can pull like that. See that? Similar to the carbonyl carbon, aldehyde ketone, something like that. Okay? So this withdrawing group, this is a moderate electron withdrawing group. All right. Compared to D, D is inductively withdrawing and also pulling with the resonance effect as well. B is the nitro group is one of the most powerful electron withdrawing group. All right. If you have to rank the rate, B should be the fastest one, followed by A, C, and D. That's how you rank them. You won't be ranking on exam. Okay. You won't be ranking. On exam we do a reaction. But you need to know like which benzene do reaction, what reaction, and which position, something like that. If you have multiple benzene, which benzene do reaction first? faster, something like that. Okay. All right, let's let's try this. Multiple substituent. We've done something like this before. Okay, done something like this before. In the top one, we're adding one bromine, of course, but which position do you think bromine will get on? Is it ortho to the methyl or ortho to the nitro group? Let's do this. Okay, I'll answer this question. If you don't know, put your pen down. Shh. I'm going to answer your question. I'm going to ask you a question. You got to answer. All right. Start with the methyl group. Ortho, para, or meta directing group. Guys, you're going to be able to say that. Come on. Ortho, para, or meta. Ortho and para. People at the back, hey, open your mouth. Do not just like be a drag. Other people are talking. You're going to talk too. One more time. Methyl group, ortho, para, or meta. Ortho and para. Okay? All right. I want to hear you saying that too. So ortho and para. Para is blocked. You see that? So we're going to talk about para in this situation. Hold on. Start with next one, the nitro group. Open your mouth. Ortho, para, or meta? This is meta of it right there. Can you see the two groups reinforces on ortho to the methyl group? That's where the answer goes. Does that make sense? Okay. This is the clear one. Next one. One more time. Start with the methyl group. One more time. Ortho, para, or meta? Ortho and para. These are ortho and para to that particular methyl group. Depends on where methyl goes. Okay. Next one. Go to the hydroxyl group. Ortho, para, or meta? One more time. What? Ortho and para. This is electron with donating group strong too. Resonance effect. Are you able to see that? The lone pair and oxygen. That's the electron with a donating group. Okay. And we have nitro group. Of course, this is meta directing group. You know where the answer goes? Right there. All right, I'll do one more. I'll have you do the rest. Okay. Isopropyl. Isopropyl is an alkyl group. Everyone follow me. This is an alkyl group. Ortho, para, or meta that directing? Ortho and para. Okay, ortho and para. Now move to the methyl group. Same thing. Ortho and para. All right, this one, this two, the two groups do not reinforce. What's the tiebreaker? Steric hindrance. That these two make sense. Okay. This is Friedel-Crafts acylation. We adding the acyl chloride and aluminum chloride, producing the we call acylium ion. Yeah. Acylium ion can attack on both positions, the carbon at the top, carbon at the bottom, but the attacking on the top one is closer to the isopropyl. Okay, and the steric hindrance. All right, so that's an answer. Do this one. Now you have to be logical. All right, isopropyl, ortho and para. Do you agree? Okay. Methyl, also ortho and para. The position that you should not do reaction on is at the top carbon. You guys know why? Yeah, that's yeah. Make sense? Too close to any big groups. Okay, so you should not do on that position. I mean, too close to isopropyl, not a methyl. If you remember that toluene, when you do reaction on toluene, the major product is on ortho isomer. Okay, so but for isopropyl, yes, you should not do it right there. All right. So the major product should go to right there. Make sense? closer to the metal. All right. That's an electrophilic aromatic substitution where benzene react with electrophiles. There are 5 reactions. Okay. All right. Question about electrophilic aromatic substitution. Is it all ratio selectivity? Donating group, withdrawing group, auto para directing group, meta directing group. Any question? People on Zoom, any question? How do you know when to put major and minor product? The question should tell you. All right, nucleophilic aromatic substitution. The next 2 reaction and the last 2 reaction in this chapter, okay, is where benzene react with the nucleophile. It's kind of odd. We got to think about this. Well, the first 5 reaction you learn is where benzene react with electrophile. Are you following? Now it's just opposite, okay? And it's quite difficult to do because benzene has a bunch of electrons too, 6 pi electrons. Aromatic compound, okay, it doesn't do reaction and add nucleophile, which is more electrons into it. It sounds impossible, okay? But benzene actually can react with a nucleophile, but very, very like special case. And you're going to see these 2 reactions right here. All right, all right, look at right here. This is the first nucleophilic aromatic substitution. Okay, there's a requirement that this could happen. Okay, all right, look at right there. So we have a hydroxyl group replacing the bromine. Okay, here's are the 2 requirements. 1, you need a powerful electron withdrawing group. We have a nitro group. Can you see that? Number 2, the leaving group and the withdrawing group must be either ortho and para. Okay? Has nothing to do with what you learned earlier. Has nothing to do with this way different. This is 2 different, it's a different situation now. Right now, reacting with a nucleophile. No sigma complex, no donating group, withdrawing group has nothing to do with it. All right? But the requirement is the leaving group and the electron withdrawing group must be either ortho and para position. Meta doesn't work. Very special case. Okay? I'm going to explain why ortho and para only. Why can't it be meta? Let me show you. I'm going to show you the rate of both both scenario. Let's say if the withdrawing group is para to bromine, you can do ortho as well. Okay, I'm going to picture the para. The first step is hydroxyl group attack. This is hydroxide. You know, you get that negative charge right there. This negative charge is delocalized around the benzene. All right. Now look at these 3 complex. Okay, this complex is similar to sigma complex, but it's a positive charge version of sigma complex called Meitner-Heimer complex. You don't need to know the name, okay, but you can see it's similar to sigma complex, but it's a negative charge version. These 3 complex, which one is stabilized the most? The left, middle, or the right? The middle. What effect are you looking at? Are you thinking of what effect? Can you see there's a resonance effect right there? Okay, there's a nitro group right there, right? Next to the negative charge, that's a resonance effect, you know? Okay, so the intermediate is stabilized. If the electron, look first, look, eyes up. The complex will be stabilized only when the leaving group, the electron withdrawing group is on para position or ortho position. Can you see that? This is the reason why the one of the requirement is ortho and para. Okay, can it be meta? Let me show you the meta. The negative charge in the Meitner-Heimer complex is not that stabilized. Just probably through inductive effect. That's it, not resonance effect. Okay. So my point is, when the electron withdrawing group is on ortho or para to the leaving group, Meitner-Heimer complex become more stable. The reaction proceeds more quickly than the electron withdrawing group at meta. So when I go forward with the top one right there, kick bromine out, that's a faster reaction. Okay. Make sense on this? Okay, very situational when the when benzene react with the electrophile, with the nucleophile. Okay, now one more thing you have to recognize. This is quite difficult, so that's why I'm not quite difficult. You don't really think about it. Okay, now look at the product right here. Do you know what this group called? This is phenol. Phenol is quite a lot more acidic than a regular alcohol. Anyone remember pKa of phenol? About 10. Okay, pKa of regular alcohol is 16. About 10 to the 6 or a million times more acidic than alcohol. Okay, now when you add a nitro group onto it, does it make phenol more or less acidic on that position? Can you see that though? When the negative charge is on oxygen, the nitro group stabilize at negative charge too. Okay, so as a result, para-nitrophenol is how many times? 1,000 times more acidic than regular phenol. So that, or 10 to the 9 times more acidic than regular alcohol. So my point is, under basic solution, phenol won't survive. It turns to be the conjugate base of phenol, the phenoxide. If you want a phenol back, you have to quench with acidic solution like hydrochloric acid, sulfuric acid. Put the proton back on. Okay. If you play with phenol, so be careful. That alcohol can be deprotonated under basic condition. Remind me, to do nucleophilic aromatic substitution, 2 requirements need to be met. What's the first one? Powerful electron withdrawing group, okay, or 2, the leaving group and the withdrawing group must be ortho or para, okay, and that's tell you it affect the stability of Meitner-Heimer complex or the intermediate. Which one? What's the product look like? What's the product look like? Who get replaced? Bromine or chlorine? Chlorine, not bromine. Bromine is more, it's better leaving group. It's a meta position, so Meitner-Heimer complex doesn't really that stable. Okay, all right. So chlorine should be replaced right here. Here's the reason why. When the methoxy group attack the carbon with the chlorine, you have that Meitner-Heimer complex. You see that? The negative charge is stabilized by the nitro group, and here's a product. If you do bromine, if you replace on bromine, you can draw any sigma complex, and you should be able to see that the negative charge is not directly next to the nitro group. The nitro group does not stabilize the negative charge through resonance effect. Okay, so the replacement of bromine should be slower than the chlorine. Chlorine should be faster. This is why chlorine is less. What's it? Living group has less living group ability. All right. All right. That's the first nucleophilic aromatic substitution. Okay. Very situational. You got 2 requirements need to be met. All right, next one. Okay, so we call this elimination addition reaction. Okay, we know that benzene doesn't really do reaction. Do a regular substitution, it does not do reaction. Too many electrons on benzene. Adding a nucleophile is not the case. Okay, to do nucleophilic aromatic substitution, like the first one, this one right here. Okay, powerful electron withdrawing group, and the withdrawing group and the leaving group must be ortho or para. Those are the requirements. Cannot do on meta. Or another situation that that benzene can react with the nucleophile is when you force it to. Look right there. How do we force it? You increase the temperature, see that? Okay, so we can force it this way too. This type of nucleophilic aromatic substitution was discovered long time ago, even before World War II. Okay, this in Dow. It's a pharmaceutical company like Pfizer, basically. This is back in the day. 1928, they found that the leaving group on benzene can be replaced by a powerful nucleophile like this. Okay. First thing first, you don't see the high temperature like 350 degrees in this reaction only because of sodamide. Very, very strong nucleophile, much stronger than hydroxide. Weighs much stronger. Okay, that's why we don't need the high temperature in this case. But let's see what happened first, right? Chlorine is being replaced by the nucleophile amide. Okay, you get aniline. So they they discover this reaction, but they don't know how what's going on, how it works. Okay, so they did some experiment. I'm going to show you 3 experimental data, and you tell me what's happening at the in the mechanism, how this reaction works. Can you do that? I heard you guys smart, right? That's how we do the science, right? We do experiment, we get data, and we come up with a hypothesis, right? We guess what's going on. I'm going to show you 3 data. Okay. Look at the first one. Let's see what does this mean. We call it just a structure modification. Okay. So instead of the bromochlorobenzene, go back one slide. That's a chlorobenzene. Can you see that? They attach a methyl group right there. Do the same reaction. Okay. They found that there are 2 products coming out. Almost 50% each. Let's assume, keep things simple, 50% each. Half and half. What does that mean? Don't lose me. Don't lose me. It's time to think. Any hypothesis? What does this mean? You put a methyl group right there. We get we observe 2 products. Think about this. If this were, this is the nucleophilic aromatic substitution, nucleophile has to attack benzene. Are you following on that? This is nucleophilic substitution, like a SN2 substitution. Nucleophile must attack something. In this case, it's going to be benzene. Which position do you think nucleophile attack? How many such positions are there? Think about that. Second experiment. We call this isotopic labeling. We label one carbon with carbon 14 right there. They can follow where the carbon, this carbon goes. Okay. Run the same reaction. They found that 50% each. How will you interpret this data? This is nucleophilic substitution. Nucleophile must attack. Eyes up, eyes up. There's an answer at the bottom, of course. How many reaction centers are there? Guess. At least 2. Are you following on that? The reason they put the methyl group right here is to put a reference position onto benzene. Are you following on that? Okay, they put a reference. It's just a benzene. All 6 carbons look the same, right? So they don't have any reference point. They put a methyl group right there, put label carbon 14 right there as a reference point. Okay, now what we found, there are at least 2 reaction centers. Does that make sense to you? Okay, all right, I'm going to show you the next reaction. Okay, so right now we know that, hey, there must be multiple reaction centers, maybe at least going to be 2. Look at the last reaction. Let's say if anyone here in this room recognize it. People on Zoom, one more, you too. Okay? Let's say in about 300 of you, anyone recognize this reaction. Now they run the same reaction, take chlorobenzene, run the same reaction, but this time they add furan. Furan look like that. Okay? They found out that, yes, they get aniline, just like what we know earlier. And the byproduct, some of this react with furan, making byproduct look like that. This is side view, this is top view of the byproduct. What reaction are we talking about? Do you recognize that? This is Diels-Alder reaction. Hold on. This is the crucial part. Put your pen down. Put your pen down. This is the crucial part. If this were to be Diels-Alder reaction, this is Diels-Alder product. What's the intermediate look like? This is very crucial. What's the intermediate look like? Can you do retro Diels-Alder from here? We've been talking about it. We've been practicing it. You know how to do retro Diels-Alder? All right. So this how they propose. Okay. They call it elimination addition reaction. The first step is elimination. Put a negative charge right there. This negative charge will kick out the chlorine out. Watch. Forming this intermediate. We call this benzene. Did you have that in your brain? Did you think about that? That's retro Diels-Alder. You should get that one. Okay. All right. Why benzene is acceptable here? Okay. Here's the reason why. Look at benzene right here. The nucleophile can attack this carbon, get that one, or that carbon, get the other one. See that? These two is identical at the moment, but if you put a methyl group on any of this position, those won't be identical. Okay. There are two reaction centers where the nucleophile attack. From the top one, pronation, you get one aniline. The bottom one, you get the same aniline. But it could lead to the two different products. Depends on the structure of benzene. Now, from benzene can react with furan, the one we add, which is additive to this reaction. Okay, we add as extra. So to trap the benzene, this is Diels-Alder reaction. Can you see that? Okay, so this is a brilliant way to determine the mechanism. This is the most acceptable way most acceptable mechanism of this type of reaction. Okay, all right, talk about benzene real quick. Okay, benzene, although we draw as a triple bond, it's not actually a triple bond. It's not. Okay, if you remember to form a pi, what orbital form a pi bond? 2p orbital, and this 2p orbital must be what? Perpendicular or parallel? Must be parallel. It's not parallel. You can make this 2p orbital parallel. Are you following on that? You cannot. It's not a p orbital either, actually. Okay, that's an sp2 carbon. That's an sp2 orbital. They are not parallel. Okay, so what is it though if it's not parallel? These two electrons behave as two radicals, and radical is unstable. You know that, right? That's what actually happened in what we consider the property of benzene. Benzene doesn't have a triple bond. Does not. Even though, yes, in bond-like structure we draw a triple bond, but it's not a triple bond. Okay, these two orbitals are not p orbital. They're sp2, and they're not parallel. These two electrons are very highly nucleophilic. I mean, highly not nucleophilic, highly reactive because it behaves as radicals. Okay, all right. From this, from what do you know, can you predict the product of this reaction? From what do you know? Now, let me help you right here if you can't really follow, okay? This one we go through the elimination addition reaction where the triple bond should be at the intermediate. You know where? Which carbon have a triple bond? This one. You see that? There should be a triple bond On the left side, the right side doesn't matter. Okay, so that's where the triple bond should be. The nucleophile can attack on either carbon or benzene of the triple bond. All right, should lead you to those two products. Sometimes can lead to 3, sometimes can lead to 3, probably the max I've seen. Okay. All right, question on this reaction? Okay. We use this reaction to add nucleophile to benzene. Okay. For example, just look at an example to make anisole from benzene. All right. This is what we do. Okay. So anisole have methoxy group on benzene. The functional group is an ether. Are you following on that? Anyone still remember from Argo 1 how do you synthesize ether? Williamson ether synthesis. Have you heard that? Okay, something like this. Start with an alcohol. See that? You can do this at retrosynthesis. All right. To add an alcohol to benzene, you can do nucleophilic aromatic substitution. What we learned earlier, but you need a leaving group. Okay, you need a leaving group on benzene. Do you know how to put a leaving group on benzene? Do you know how to put a leaving group on benzene? Yes. Okay, you can do chlorine, you can do bromine. Okay, bromination, chlorination, right? Something like this. Right? So when you do chlorination, you can do bromination, put one leaving group, functionalize benzene. Just like a radical reaction, we use radical reaction to functionalize alkane. So you can do things on it. Okay, very important reactions. All right, add a leaving group on things. All right. From bromine right here, you can do nucleophilic aromatic substitution. What we just learned, elimination, addition reaction. I'm going to keep repeating the name so you know what I'm talking about. Okay, so so we have a hydroxy group replace bromine. Okay, but be careful. This is under basic solution. Phenol can survive. You get the phenoxide under basic solution. So you have that. From right here, add a methyl group SN2 reaction. You get an anisole. Okay. Some of you may ask, can I use put a methoxy group right here? Yeah, it might work too. Instead of you go through two step like this, it might work. Just replace sodium hydroxide with a methoxy group, like sodium methoxide. Okay. We use elimination addition reaction. This reaction we're talking about is not effective when benzene is functionalized. When the benzene have a substituent. For example, if you have toluene, if you have anything on benzene already, okay. Let's say you try to do the elimination addition reaction. What happened is this guy will behave as a reference point. When you go through a benzene triple bond, there will be 2 reaction centers. And it'll lead you to multiple products. Look like that. See that? It won't be effective when there are things on benzene already. Yeah, we usually use this reaction probably on a regular benzene only, like naked benzene, nothing on it. Okay. All right, let's summarize the reactions that you learned. Okay. Check this out. Are you familiar with any of this? Look hard, look and think hard. The top one in red, these are the reactions we learned in this chapter. Are you following on that? Yeah, and the bottom one mostly, not all of them, but mostly this what happened at the benzylic position. Okay, there's a Clemmensen reduction. Have we talked about Clemmensen reduction? Okay, in this chapter. All right. In this chapter, we'll learn 3 synthetic strategies how to do synthesis. Okay, I will teach you 3 ways to do synthesis. The first one is called the use of protecting group. Have you used protecting group before? Yeah, a little bit in Argo 1. Okay, maybe I'm not sure you remember, but a little bit of it. But very similar idea. Well, pretty much the same idea. Let me show you first why we need why we need protecting group. How do you know when you need protecting group and how to do it? I'm going to teach you all this. Okay, let's look at this reaction. If you do bromination on tert-butylbenzene, Is third butyl group ortho, para, or meta directing group? Guys, one more time. Hey, people in the back, I'm asking you too. Open your mouth. Ortho, para, or meta directing group? Ortho and para. Which one is a true major, ortho or para for the third butyl? Should be para. What's wrong with the ortho? The steric hindrance. Okay? If you do this reaction, para should be the major product. Should be. All right? Ortho is going to be low yield. Now, here's a situation. What if you want the ortho product? Okay? What if you want an ortho product? Well, we will have to block the para position. Does the logic make sense to you? You can get both ortho and para. Para is a major product, right? In this reaction. Okay? Let's say we want just an ortho. What do you have to do? Let's say, can we block the para? All right, that's the situation we're talking about right now. So we will use protecting group in this situation. Okay, the property of protecting group is easily to install and easily to remove. Does that make sense? That's a protecting group. You can add on, you can take it out. All right. So it looks like the scheme will look like this. You adding protecting group, add para position, functionalization, do whatever you want, and then remove the protecting group. Okay. Whole protecting group have this idea. They all do like this. All right. Here's how they use. Here's the protecting group. Are you familiar with this reaction? The top one. Eyes up. The top one. We call sulfonation. Okay. We have learned the reaction mechanism already. All right. Going backward. Look right here. These two, the product benzene and the sulfonic acid on benzene. These two are in equilibrium, which allow you to control if you want the product or you want the reactant. You have the ability to control by Le Chatelier principle. Okay. If you want to go forward, okay, what do? You add concentrated sulfuric acid. What does concentrated mean? A lot of water or little water? Concentrated sulfuric acid. Little water. Okay. So you can see that if you go forward, there's no water at all. When you go backward, add dilute sulfuric acid. What does dilute mean? A lot water or less water? A lot water. We flood the sulfuric acid out with water. Can you see that? They are in equilibrium. Okay. So we're gonna go backward now. If you remember the forward reaction, the reverse reaction, it's just tracking back. When you go forward, there's a nucleophilic attack on sulfur trioxide, and then re-aromatization, deprotonation. Remember that? When you go backward, what's the opposite of deprotonation? It's protonation. The first step, go backward, is protonation. And the second step, going forward, is a nucleophilic attack. When you go reverse, it's a loss of leaving group. It's reverse. Okay? Here's the mechanism look like. The first step is protonation. You know? All right, you go back to the sigma complex, is it up? And then loss of leaving group. You get sulfur trioxide out. This is the mechanism going backward. All right, that's how it works. Let's talk about how to use in synthesis. Okay, that's more important than just draw mechanism. Doesn't do anything. All right, here's the synthesis. All right, again, just remind you, right now we want an ortho, not a para, okay? But if you run this reaction just that, you're gonna get para. So we have to block at para position. So we block it with sulfonation, okay? Why can we block para in this situation? Well, because third butyl direct an incoming electrophile to para position more than ortho due to steric hindrance. Are you following on that? Just as we predicted, para is gonna be the major product, okay? Ortho going to be less minor product. We can remove ortho through whatever purification process you do. All right, take the para and move forward. Okay, we functionalization, do whatever you want, and then remove the sulfuric acid by adding a lot of water. Flood them out. Does the idea of protecting group make sense to you? Okay. Let me show one more time. I'll do this one more time, okay? I have two examples. I'll do the first one and have you do the second one. Can you do that? I'll do one more time, okay? Watch closely. Put your pen down. Just put your pen down. An idea you should get from this slide is how do you know you have to use protecting group, or when do you know you need protecting group? Are you following on that? You got to recognize that first. Okay? How do you know you need protecting group? What gives away? Well, for sure, we're doing bromination on benzene. Are you following? We add bromine, and what else do we add? We add bromine, and what else? We call ferric bromide, FeBr3. Are you following on that? That's what we have to add. But if you do straight bromination, where do you think bromine goes? All right. Now you can look at the benzene. They said donating group, that's withdrawing group. Can you see that? If you do electrophilic aromatic substitution, whatever you do, which position gets the electrophile? Number 3. Does it make sense? Okay. The green one, the donating group, is ortho and para. The red one is meta only. See that? We combine everything you learned. Okay. So if you do straight bromination, you're gonna go to 3. Do we want 3? No, we want number 1. We want number 1. So we have to block number 3. Does that make sense? This is when you know you need a protecting group. Okay, and that's very important because you have to recognize that, hey, we are in this situation, we need a protecting group. All right, let's do this. So we need a protecting group, so we can do sulfonation. Okay, adding a sulfur trioxide and a lot of sulfuric acid, little water. Don't add water in this case. Okay, so you're going to put sulfonic acid onto the position 3. Yes, position 1 also gets sulfonic acid too, but not a lot. Para is a major product, right? All right, we'll take para and move forward. Okay, do bromination. And then remove the sulfonic protecting group. We don't need anymore. Add a bunch of water, flood them out. Dilute sulfuric acid and heat. Do you know when you need to use protecting group? Okay, and how to use it. This is how to. Protection, functionalization, and deprotection. It goes like that in order. All right, your turn. I'm going to leave the first one right here so you have an idea of what's going on, how to use it. I would rather you move to the next one, don't just keep copying this. Do the next one first. Do you know how to make aniline? Do you know how to put an NH2 group, amino group on benzene? You have to go through nitration like that. Does it make sense to you? This is the only way so far to make an aniline. You got to go through nitration and then reduction. Okay. All right. These are the drill always. All right. If you do nitration, straight nitration, where do you think the nitro group go? You know which position? Which one? 1, 2, 3, or 4? If you do straight nitration, should be 2. Should be 2. We don't want on 2, we want on 4. See that? So 2 must be blocked. Everyone follow me? Okay, the number 2 should be blocked. Okay. All right. So electron donating group go to 2 and 4. Ortho and para directing group. The electron withdrawing group go to 2 and 4 only. They reinforce one another. This one clear. Okay, but the position 2 have to be blocked. All right, we block it first with a sulfonic acid group, sulfonation. Okay, after we block that, all right, so functionalization, so we add nitro group onto position 4, only 4. All right, and then remove the sulfonic acid group. Okay, are we done yet? Nope, not yet. Okay, so we still have to convert nitro group to the amino group. Here we go. Yes.
How do you complete the Lewis reduction without the O1 oxygen?
How do you what?
How do you reduce NO2 group to NH2 without reducing the eternal?
This is not Clemmensen reduction. This is not. This is selectively reduced nitro group only. The last 2 steps can be swapped. The only reason I put the reduction at the end is, think about this. If you do, okay, from right here, if you reduce the nitro group to amino group first, yeah, you'll get the amino group right here with the sulfonic acid on it. Are you following on that? Now, look at the reaction condition of the sulfonic acid to remove sulfonic acid. Look right here. Acidic solution or basic solution? One more time, acidic or basic? This is acidic solution. Having amino group under acidic solution, what do you get? You get ammonium ion. Does that make sense? I mean, it's fine. And then you have to add sodium hydroxide one more time. Just add things a bit longer. Okay. All right. That's how to use protecting group. Okay. All right. 2 more synthetic strategy. Next one, we call this an order of reaction. Order matters. All right. Look, for example, right here. I'll look at this too. From benzene, there are 2 steps you have to do. One is nitration. The other is bromination. Everyone follow me. If you follow me, say I. Okay, there are 2 steps you have to do, but which order? Which order will lead to the product? Let me show you though. Okay, all right, there's 2 steps you have to do. Bromination first or nitration first. Got 2 ways. If you do that, let's say bromination first. Now I put bromine onto it. What type of directing effect does bromine have? Ortho, para, or meta? It's ortho and para. Okay, if you do nitration, it's going to go to that. You're not going to get to the product. See that? If you reverse, let's reverse. Oh, one more thing. Some people, like just for some of you ask, okay, adding in first nitro group, can second nitro group get on benzene? In theory, yes, it can, but it's less likely. Here's the reason why. Start with bromine. Is bromine activating group or deactivating group? Deactivating. What does deactivating means in this in a reaction situation? Faster, slower reaction. Slower, okay? Adding bromine, this benzene is less or is slower than the first benzene, the starting benzene. Next one, adding a nitro group onto it. What does nitro group do? Activating or deactivating? Deactivating, right? Nitro group is even more powerful than bromine. This benzene, the product right here, is sluggishly slow to do reaction. The second nitro group is very difficult to add. Does that make sense? Right? Yes, on paper, you can just draw anything on it. But in reality, you can add the third or the second nitro group, but it's going to be very, very slow. So that's why you don't have to worry about it. Does that make sense? Okay. All right. Let's do the other way around. Okay. Start with the nitro group. So add the do nitration first. You have nitro group on benzene. What type of directing effect is a nitro group? Meta. When you do bromination, you go to meta. See that? Can this happen? Can this happen to bromine groups? I mean, it can, but like, is it likely? Less likely? Less likely. This benzene, when we have nitro group and a bromine on it, 2 withdrawing group, that benzene gonna be very, very slow now. I wouldn't worry about the third electron withdrawing groups. Okay. All right. So the order matters here. Okay. Let's do this one together. What order? Well, there's one is a chlorination. What's the other reaction? What do we call it? The other reaction? Friedel-Crafts acylation. Okay. All right. What should you do first? Just think about it. Don't have to write down. Think about it. What should you do chlorination first, or should you do acylation first? Chlorination. Why would you say chlorination first? The product is ortho and para to one another. No, it's para to one another. Can you see that? So you need an ortho or para directing group. Okay. All right. So you do chlorination first. Put chlorine onto it. Chlorine is an ortho and para directing group, and then Friedel-Crafts acylation. Okay. The para should be the major product as we know it. All right. Now, if you do the other way around, so acylation first, well, the AC group or this ketone is a meta directing group, you're not going to get the product. Doesn't work. Do you recognize that the synthesis have logic? Do you recognize that? Okay. When you practice synthesis, don't just like whatever. You got to think. You got to force yourself to think. Okay. There's no way around it. Louder. Use protecting group to make para? No, protecting group is used to make ortho. You will block the para to get ortho. All right, the last one is reverse directing effect. A same directing effect, but you can reverse it. Okay, you have an ability to control. All right, now let's look right here. There are two things you have to do: installing bromine. You know that reaction. The other one is installing the amino group NH2. How do you make a nitro group on, or how do you make the NH2 group on benzene? You go through nitration this way. Remember that? You go through this way. Okay. All right. Let's say you do the making aniline first. So you're gonna go through this drill, same drill. Now, everyone, look at aniline. NH2 group. What type of directing effect is it? You gotta recognize that. What type of directing effect is it? Ortho and para. Okay, this is ortho and para, which means that if you add the bromination right here, you're not gonna get to the product. Does that make sense? You're not gonna get to the target molecule. Okay, so go back right here. Go back right here. So what else? What if you put bromine on first? Can you do that? Would you get to the target molecule? No, right? Because bromine is also ortho and para as well. The product is meta isomer. You need a meta directing group. Does the logic make sense? Anything here is meta directing group. The nitro group right there. See that? So this is what you do. Don't make aniline yet. Do not make aniline yet. Add the nitro group. Stop right there, and then do bromination first. Let's sneak its way to it. Okay, do bromination first, and then when you're done, okay, all right, we don't need nitro group anymore. Okay, remove it, reduce it to aniline. We call this reversing directing effect. So that you can change the directing effect like this. Let me show you what type of groups you can be used to change directing effect. Okay, answer the question one more time. Put your pen down. Put your pen down. I want to hear you say it. Okay, nitro group, ortho, para, or meta. This is meta. Change it to aniline. This is ortho and para. See that? Directing effect change. Okay. Next one, methyl, ortho, para, or meta. This is ortho and para. You can do this. Carboxylic acid is a meta directing group. It's an electron withdrawing group. See that? Next one, go to ketone. Ketone like acyl group, ortho, para, or meta. Hey, ortho, para, or meta. This is meta. Okay. You can do Clemmensen reduction. Reduce it to regular alkyl group like a methyl. This is ortho and para. Lastly, back to toluene. This is ortho and para. You can do this. What are we doing? Convert this guy from donating group to withdrawing group. Can you see that? And this is meta directing group. That's how it works. Okay. All right, put your pen down. I'm not gonna let you need this one. I'm gonna have you think about it. It's all about thinking right here. Okay, the logic. We want to get the logic today, not much about the answer. There are multiple answers most of the time. Okay, look at right here. There are two tasks you have to do. One is converting the methyl to carboxylic acid. That's one. Are you following? You know what reaction that is? Think. Do you know what reaction that is? That one. The other one is sodium dichromate. It's the same thing. You got two recipes, right? You can use either one on exam. That's one task. Oxidation, methyl to carboxylic acid. Two, do nitration. What do you do? What do you do first? Should you do nitration first or should you do oxidation first? You should do what? Oxidation first. Why you need to do oxidation first? You need a meta directing group. That's it. That's all you need to know. That's all you need for this type of reaction, synthesis. Does that make sense? The rest is gonna be come up with a synthesis, synthetic plan. Okay. So all right, oxidation first. This is auto and para. Can't use that. All right, convert it to meta directing group. Okay, you can use the other recipe too, sodium dichromate. Okay. All right, this is meta directing group now, so we do nitration. That's it. If you understand it, it's not that complicated. Just the order. All right. All right. One thing you need to know, there's a couple limitations you have to know, and you wouldn't notice, okay, on paper, because anything could happen on paper. You can write things out. Does that make sense? Anything could happen on paper, but here's a limitation that we observe in practice, okay? And you can do this on exam. You cannot do the following on exam. All right. Here's the first one. Friedel-Crafts type reaction, acylation, alkylation, either way, okay? Friedel-Crafts type reaction cannot be done when benzene has highly deactivating group, like a nitro group, okay? Or moderate deactivating group. It doesn't work. Here's the reason why. Here's the reason why. Answer this question, please. Eyes up. Eyes up. Hey. When you add these two together, acyl group and aluminum chloride, we make a powerful, highly reactive intermediate called, start with an A. Acylium ion. You have that in your second note. We call the acylium ion. Look something like this. Okay. Acylium ion is electron poor. It's electrophile. Can we agree on that? Electrophile means electron poor. Acylium is an electrophile. It's electron poor. Okay. Now look at benzene. If benzene has electron withdrawing group onto it, benzene become electron poor as well. Poor people, they're not going to get rich. Does that make sense? It's a bad analogy. It's not. Okay. But you get an idea. You cannot put electron poor species and another electron poor species and hope that there will be a reaction. Reaction occur between the electron rich and electron poor. Electron rich use HOMO. Remember that? Electron poor use LUMO. They have to react like that. One partner, at least one partner, is gonna have electrons. You have a poor electron is not gonna do reaction. That's the reason why. Okay. So another one doesn't work too. When moderately deactivating doesn't work as well. Can't do that. You can only do Friedel-Crafts type reaction when benzene is slightly deactivated. This is acceptable in practice. You can do reaction. Not talk about the yield. The yield probably bad, but it's okay. There'll be reaction. Or we love this one, highly activated benzene. A lot of electrons on benzene. Yes, you can do that. Okay. So when you do Friedel-Crafts type reaction, be really careful. I'm going to test you on the next example. You cannot do Friedel-Crafts type reaction. When again? When benzene has highly withdrawing or moderately withdrawing or deactivating group. Okay. So you cannot do in these two situations. Now, the last one you have to be careful is when you're dealing with aniline. Okay, aniline should be the last thing you make, because here's the reason. Aniline is reactive. Look at what happened. Okay. All right. This reaction, you have seen this reaction before. We call nitration, right? Put a nitro group on benzene. It doesn't work on aniline. Here's the reason why. Are you familiar with this sign? Oxidizing agent, right? just a little bit on a side note, any compounds, okay, that has high oxidation number, they are oxidizing reagent. For example, manganese. Have you seen do an oxidation reaction on manganese? Copper, like transition metal, high oxidation number. Okay. Nitrogen and sulfur, like nitric acid and sulfuric acid, they have high oxidation number. They can do side reaction like oxidation reaction, and it can do oxidation reaction on aniline, and it turned to be something else that we don't know. So you cannot do that. Okay. All right. Some of you are like, how do I know? I mean, like, that's why I'm telling you. Okay. So another reason you should, if it doesn't make sense to you, it's fine. It's cool. I have another reason why you should not do this reaction. Okay. Now, question to you. Look at aniline. Hold on. Look at aniline. Is aniline basic or acidic? Aniline. Guys, amine, acidic or basic? Basic, right? You had an acid. The side reaction is pronation. When you do pronation like that, from donating group to withdrawing group, can you see that? And the reactivity of benzene change from ortho para-directing group to a meta-directing group. You're not going to get to the target molecule. You have no control on that. Okay. So my point is, when you have an aniline, it's a base. You cannot add an acid directly onto it. Otherwise, acid-base reaction happen first. So you have to be careful. Okay. Later, in the next two chapters, you'll be doing reaction with aniline. The only way to do reaction on aniline that doesn't let aniline interfere with reaction, we have to protect aniline first. That's it later, the chapter 20. Right? So we're not there yet, but we can, but that's later. All right. Let me do this one. I'll have you do the other one. Okay, I have two examples. I'm going to do this one for you. Okay. All right. There are two tasks you have to do. Can you see that? The first one is adding aniline. To make aniline, what reaction you have to go through? Nitration. See that? It's the same thing. I'm trying to repeat it. Okay. It's the same drill. That's biologic. That's only tools that you have. You're going to go through nitration. Okay. Right here, you can add this to benzene. What reaction? Either alkylation or acylation. Friedel-Crafts reaction. Doesn't make sense. Should you do alkylation or acylation? You should do acylation in this case. Why you should not do alkylation in this case? There might be a rearrangement. If you know it, excellent. Okay. So we have to do acylation and Clemmensen reduction. Go through that. So you got two tasks you have to do. The question is, in which order? What tells you which order you should do? What tells you? The products, see that? They are meta to one another. Can you see that? So whatever you do, you gotta go through the meta directing group. Okay, and use that to get to the target molecule. Okay, it gotta be meta. All right. All right. Let me show you first. Okay, so you got two tasks. Let's say you do nitration first. Here's a nitration. You get that, right? And then we do acylation. Okay, can we do acylation? Can we do acylation? No. Friedel-Crafts acylation cannot be done when benzene has what? Highly deactivating group or moderately deactivating group. Look at the nitro group. What do you know about nitro group? Highly deactivating. You cannot use that. So no, you cannot do Friedel-Crafts tie reaction in here. Okay, so no. Let's do acylation first. Let's start with acylation. All right, put the AC group onto it. This is a meta directing group. Can you see that? Okay, from right here, let's do nitration. That works. Lastly, Clemmensen reduction. Reduce that. Right? Or I have to reduce both of them. Okay, now last step right here, you have to reduce the ketone group. Then you have to reduce the nitro group. Can you see that? Let me show you the magic. To reduce the nitro group, we go through this set of reagents. To do Clemmensen reduction, reducing the acyl group, you go through this set of reagent. Can you see the similarity? Okay, so what you do, just combine these two. Use zinc, that's a hydrochloric acid, add heat in one step. Bam. You can do that too. And feel free to do that on exam. I mean, you're going to practice on a study guide. You're going to see this a few times. Okay? You can do either or. All right? All right, your turn. There are three ways to start the synthesis, right? You can either do bromination first, nitration first, or acylation first. Okay? Which one do you do first? Acylation, bromination? Okay. All right. If you have your answer, okay, can you tell me why should you not start with the other two reaction? You're gonna get to the very detail. Well, you have your own synthesis, yes, but why should you not do the other two? Can you see that though? You don't have to answer, but can you see it? I want to have you to try to have you practice analyzing it. There are three way to start: bromination, nitration, acylation. Only one of them work. The other two do not. But why though? I want you to see it. I mean, if you start that way, I mean, what would happen, right? All right. We call this retrosynthesis. That's why we've been doing it, okay? So you should practice retrosynthesis, not just like try to go forward. So sometimes it doesn't really work that way. You got to think about it, okay? All right, so there are three things you have to put on this benzene, okay? I'm going to take one thing out at a time. Let's say I take bromine out. The step before adding bromine, you're going to go through that intermediate. Are you following? Okay, I'm going to remove one bromine. So the intermediate before the target molecule is going to be that one. If you have these two and add bromine, does it work? No, it doesn't work. It's going to go that way. So bromine cannot be at the end. Bromination cannot be done at the end. Okay? All right, next one. All right, removing the acyl group. Remove that. You're going to go through that intermediate. That's the last intermediate before the target molecule. Can you do acylation right here to get to the target molecule? Remember the limitation. Acylation cannot be done when highly deactivating and moderately deactivating. Nitro group is highly deactivating. Add bromine onto it, it's weak, but add on these two together, that benzene is useless for acylation, not for other reaction. Okay, so can't do that, and it will go that way too. It doesn't work. Okay, all right, let's remove the nitro group first. Okay, this is the last intermediate before the target molecule. Can you do nitration on this guy? Yes, you can. You can do nitration on this guy. You're gonna go that position, ortho position, meta position, right there. Yes, you can. So it looks like nitration should be last. Okay. All right. Compare between these two. Should you do bromination first or should you do acylation first? Bromination gotta go first. Okay. Because take a look. If you start with if you do acylation first, you cannot put bromine on para position. Make sense? Okay. If you do acylation, do bromination first. This is ortho and para directing group. So yes, you can do acylation right there. So here's a synthetic scheme. Okay. You do bromination, followed by Friedel-Crafts acylation. You know, this is ortho and para directing group. You get AC group right there. Okay. And then finish with nitration. A lot to learn. All right. See you Wednesday.